AI feels invisible. You type a prompt, wait a split second, and boom, a highly complex answer just magically appears on your screen. But behind every single answer, there is a physical machine using electricity, producing heat, and demanding cooling. And that hidden reality is exactly what we're digging into in today's explainer.
So, if artificial intelligence is essentially just software, just code, data, and algorithms, why on earth does it need so much electricity? It's a huge paradox, right? We're suddenly talking about gigawatts of power and massive infrastructure strain. Well, every time you send a request to a generative AI model, that request doesn't just float freely in the digital ether. It actually triggers a massive physical chain reaction in the real world.
Because here's the absolute truth. The cloud is not weightless. It is a massive, heavy, and incredibly power-hungry physical system. The big question we face today isn't just whether AI software can get smarter. It's whether our physical world, our actual power grids, our local water supplies, and our cooling infrastructure can actually support the massive machines that make that intelligence possible.
Section 1. The physical reality of AI.
To really wrap our heads around the engineering challenge ahead of us, we have to look at the macro scale, 415 terawatt hours. According to the International Energy Agency, or IEA, that's the estimated amount of electricity global data centers consumed in 2024. To put that massive number into perspective, that is about 1.5% of total global electricity use, just to keep the lights on and the servers humming.
And we are accelerating so fast. The IEA's base case projects that by 2030, global data center electricity consumption could more than double, hitting around 945 terawatt hours. That would capture just under 3% of all global electricity use. Between 2024 and 2030, electricity demand from these data centers is projected to grow at around 15% per year. That is literally more than 4 times faster than the growth from all other sectors combined.
Now, this isn't just a global issue. It's a massive domestic infrastructure challenge, too. The Department of Energy reported that U.S. data centers used about 4.4% of total electricity in 2023. But watch what happens by 2028. That could surge to anywhere between 6.7% and a staggering 12%. Load growth has already tripled over the past decade, and it's being driven heavily by these new AI workloads.
Section 2. The hidden AI system.
So, to understand those massive macro numbers, we really need to deconstruct exactly what happens in the physical world when you interact with AI. It's basically an invisible chain of events. Step 1. You type a prompt. That data travels through fiber optic networks straight into a sprawling data center. Inside, specialized AI chips perform massive mathematical computations to actually formulate your answer. Now, those chips consume electricity. That electricity becomes heat. That heat requires immense cooling systems. And all of that power, it's pulled directly from the local electricity grid.
Section 3. The mechanics of heat. You might be wondering, why do AI workloads demand so much more energy than the traditional internet we're used to? Just look at this contrast. A standard web search uses roughly 0.3 watt-hours, but a single generative AI query, that requires about 2.9 watt-hours. It takes nearly 10 times the power. It's kind of like the difference between asking someone for quick directions versus asking someone to instantly write you a novel while doing complex calculus. When you multiply that by billions of prompts a day, those tiny watt-hours snowball into massive gigawatts.
Think of it this way. An AI chip is essentially a high-performance engine. The harder it works to learn from massive data sets during its training phase, or to answer millions of daily user prompts, the more fuel, meaning electricity, it needs. And just like a huge engine, all that continuous, intensive calculation produces a tremendous amount of exhaust in the form of heat.
So let's look at how this translates to the actual hardware. For years, data centers were built around general-purpose CPUs. Those would pull a totally manageable 5 to 12 kilowatts per server rack. But modern AI relies on specialized GPUs built for massive parallel computation. They're doing thousands of tasks simultaneously rather than just one at a time. Because of this, modern AI server racks pull 60, sometimes well over 100 kilowatts per rack. It is a tenfold explosion in localized power density. A single rack of these servers can draw as much power as an entire neighborhood. And remember, every single watt consumed turns directly into heat.
Section 4. Straining the power grid.
This localized microscopic chip problem quickly escalates, straining our macro power grids and pushing us right up against real-world engineering limits. Because at the end of the day, intelligence creates heat,
and heat becomes an engineering problem. The laws of thermodynamics dictate that all this new electrical computation ultimately has to be removed to prevent catastrophic equipment failure. If you don't exhaust that thermal energy fast enough, these multi-million-dollar servers will literally melt down.
These are the physical bottlenecks data center operators are facing right now. AI workloads are dramatically increasing the pressure. We're talking about the huge challenge of securing grid connection capacity in places where power lines are already totally maxed out. We're looking at high-density cooling demands that guzzle millions of gallons from local water supplies. Plus, there is the absolute necessity of reliable, firm, 24/7 power generation to keep these models running without a single interruption.
Section 5. The future of infrastructure.
So what changes next? How do we actually solve this bottleneck? Well, the industry is aggressively adapting, honestly because they have no other choice. To handle these crazy high-density heat loads, we are seeing a major shift away from traditional air cooling and toward advanced liquid cooling systems. Hardware manufacturers are also racing to design more energy-efficient chips. But beyond just the servers, facility operators are having to completely upgrade their power distribution and actively deploy clean, firm energy generation to meet these immense loads. It's a massive, highly physical rebuilding process.
Now, it's important to remember that this relationship isn't purely a one-way street. AI itself is actually being deployed as a tool to solve some of the very grid challenges it contributes to. Because AI is so incredibly good at complex pattern recognition and forecasting, it is actively being used to optimize our power grids, improve energy forecasting, and intelligently manage overall electricity demand.
We've covered a ton of ground today, but if you take away just one thing from this explainer, let it be this. AI may feel like the most digital technology ever created, but its future will be decided by very physical things: electricity, heat, water, chips, and the grid. It's not just about algorithms anymore. It's about whether our physical infrastructure can keep up. Thanks for exploring this with me today. Keep questioning the systems around you, and I'll catch you in the next explainer.